Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. To find the number of stereoisomers for substituted cyclopropane rings, we identify stereocenters and apply rules for geometric, CIS strands, and optical, enantiomeric, isomerism in cyclic systems. Each carbon of the cyclopropane ring bearing to different substituents, including the ring carbons themselves as part of the substituents, can be a stereocenter. Case: one cyclopropane with one carbon bearing substituent A, another bearing to be substituents BB, and the top carbon unsubstituted HH. The carbon bearing A has substituents A, H, and two ring bonds to different carbons, one bearing BB, one bearing H2. This carbon is a stereocenter. The carbon bearing BB has two identical substituents, so it is not a stereocenter. The top carbon, H2, is not a stereocenter. With only one stereocenter, there are two stereoisomers, R and S enantiomers. Answer A is equal to 2. Case: 2 cyclopropane with A on one carbon, B on another carbon, top carbon unsubstituted. Two ring carbons each bear one unique substituent, A and B respectively, plus a hydrogen plus two ring bonds. Each of those two carbons is a stereocenter. With two stereocenters, maximum is equal to 2 is equal to 4. We check for meso, since the two substituted carbons bear different groups, A versus B, no meso form is possible. So all four stereoisomers are distinct. CIS, R, S, CIS, S, R is equal to enantiomer pair, trans, R, R, trans, S, S. That gives 4 stereoisomers. Answer B is equal to 4. Case: 3 cyclopropane with A on bottom left and A on bottom right, top carbon unsubstituted. Two ring carbons each bear substituent A plus H. With two stereocenters bearing identical substituents, maximum is equal to 4, but meso compound is possible. The CIS isomer, A CIS, has a plane of symmetry and is a meso compound, a chiral. The trans isomer gives an enantiomeric pair, R, R and S, S. So total is equal to 1 meso plus 2 enantiomers is equal to 3 stereoisomers. Answer C is equal to 3. Case: 4 cyclopropane with A on top, A on bottom left, B on bottom right. 3 substituted carbons, top, A, H, bottom left, A, H, bottom right, B, H. 3 potential stereocenters. Maximum is equal to 3 is equal to 8, but we must check for symmetry mesoforms. The two carbons bearing A are equivalent in terms of substituent type. Systematic enumeration of CIS-trans relationships among the 3 carbons configurations can be all CIS, 2 possibilities of partial CIS-trans, alterans. Accounting for mesoforms, the molecule has a potential mirror plane when the two A-bearing carbons are related by symmetry, some pairs collapse. Detailed analysis yields 4 distinct stereoisomers. Answer D is equal to 4. Case: 5 cyclopropane with A on top, B on bottom left, D on bottom right, all 3 substituents different. All 3 ring carbons bear one unique substituent, A, B, D, plus H, making each a stereocenter. All substituents are different, so no mesoforms are possible. Maximum stereoisomers is equal to 3 is equal to 8, and since no internal symmetry exists to reduce this number, all 8 are distinct. Answer E is equal to 8. Case: 6 cyclopropane with A on top, A on bottom left, A on bottom right, all 3 same substituent. All 3 ring carbons bear the same substituent A plus H. The molecule has high symmetry. The possible arrangements are all CIS, all A on same face, which is achiral due to C3V symmetry and the alternates arrangement 1A up, 2A down or equivalent, which due to the C_S symmetry of the ring is also achiral, giving an enantiomeric pair. Re-evaluating, with all three substituents identical, we have the all-CIS isomer, one stereoisomer, achiral, and the isomer where one substituent is on one face and two on the other. This has a mirror plane, the plane through the top carbon and the midpoint of the bottom bond, making it achiral too. So there are two distinct stereoisomers. Answer F is equal to 2. Therefore, the correct answer is a 2B4 C3 D4 E8 F2. The correct answer is shown on screen.